Okay, good morning. Welcome to the class. Today, let's have a look at the third lesson of chapter 6, which is about intersection of lines in 2 space and 3 space. So first of all, let's give it an overview of today's learning goals. After this lesson, you are expected to be able to determine if 2 lines intersect at only one point or if they are coincident or parallel in 2 space. Find the distance of 2 lines if they are parallel in 2 space. Find the coordinates of the point of intersection of 2 lines if they intersect at only one point in 2 space. Then determine if 2 lines intersect at only one point or if they are coincident, parallel, or skew in 3 space. We'll have a look at these concepts later in this class. Find the coordinates of the point of intersection of 2 lines if they intersect at only one point in 3 space. Then last, find the distance between 2 parallel or skew lines in 3 space. Okay, first, let's have a look at the intersections of lines in 2 space. In 2 space, there are 3 possibilities for the intersection of 2 lines and the related system of equations. So this is not very hard to understand, right? The 3 cases are, first, the lines can intersect at a point. So there is exactly one solution, which is shown here in the graph on the left. And the 2 lines can also be coincident, which means these 2 lines are exactly the same. So there are infinitely many solutions, which is shown on the graph in the middle. And these 2 lines can also be parallel. So be parallel and unique, which means they are parallel, but they are not on top of each other. So there is no solution to this system, right? Okay, so have a look at these 3 cases here. Do you have any questions? Okay, so to decide if lines intersect at a point or they are parallel and unique or they are coincident, we can combine the equations of these 2 lines and check if there is any solutions. Okay, so now let's have a look at this example here. Classify each system as having 0, 1, or infinitely many solutions. Okay, I'll give you 4 minutes to consider these 2 questions. Okay, let's have a look at the solution together. So for question A, there are two methods we can use to solve it. First of all, we can combine these two equations to form a system and check if we can have any solutions to the system of two linear equations. So let's label these two equations as 1 and 2. We can eliminate the x by using 3 times equation number 1 minus 2 times equation number 2, which gives us 0, y equals 0. So this equation is true for all values of y. So there are infinitely many solutions, right? All of the points x, y can satisfy the original equations. Also, you could use geometric thinking. Examine the normals to the lines. A normal vector of line 1 is n1 equals 4, negative 6. And a normal vector of line 2 is n2 equals 6, negative 9. Therefore, we can see that n1 is 2/3 of n2. That means the normals are parallel. So the lines are either parallel or coincident. So if L2 is multiplied by 2/3, the result is L1. The lines are identical, right? We can observe this by checking their scalar equations. So actually, these two equations are equivalent. Therefore, they intersect at indefinitely many points. Okay, for question B, again, there are two methods we can use to solve it. First, we can use algebraic thinking by combining these two equations to form a system and then check if we can find any solutions to that system. So let's label these equations as equation number 1 and 2. And then write equations in the parametric form. X equals 1 minus 6s, y equals 5 plus 8s. The second equation can be written as x equals 2 plus 9t and y equals 1 minus 12t. So equate the x and y variables, gives us system numbers 3 and 4. So we can use equation number 3 and 4 to solve for s and t. Well, actually, you can use 4 times equation number 3 plus 3 times equation number 4. So that gives us 8 equals 0s. Apparently, there's no solution to this equation, right? This equation is true for no values of s. Therefore, there are 0 solutions to the system. If there are 0 solutions to the system in 2-dimensional space, that means these two lines must be parallel, right? Otherwise, they are coincident or intersect at a certain point. Okay, you can also use geometric thinking like this. The direction vectors of the line are m1, which is negative 6, 8, and m2, which is 9, negative 12. Since m1 equals 2/3 of m2, the directions are parallel. The lines are either parallel or coincident. Then we can check a point that is on line L1. If this point is on line L2 as well. If it's on L2, that means these two lines must be coincident. Otherwise, these two lines must be parallel and unique, right? So check point 1,5. We can insert it to the equation of line L2. This gives us t equals negative 1 over 9 for x coordinate, and for y coordinate that gives us t equals negative 1/3. Therefore, there is no single value for t. can satisfy both the x and y coordinates. That means there is no solution for this point on the equation for line L2. Since the values for t are different, 1, 5 is not on equation number 2. The lines must be parallel and distinct. Therefore, there are 0 solutions to the system. Okay, do you have any questions? No? Okay, good. Then let's consider another example here. Can you find the distance between the two parallel lines? Why these two lines are parallel? Because if you look at their direction vector, -6, 8, and 9, -12. Actually, -6, 8 can be expressed as a scalar times 9, -12, right? You can just times -2/3 to 9, -12 to get -6, 8, right? Therefore, the two direction vectors are parallel. So these two lines must be parallel or coincident. Also, you can check whether this point 1, 5 is on this line 2, 1 plus t times 9, -12. If you check that, you can see that this point is not on that line. So that two lines must be parallel, right? So if you are told these two lines are parallel, can you find the distance between the two parallel lines? Means distance from A and B. AB is perpendicular to line L1 and to line L2. Okay, I'll give you 5 minutes to have a look at this solution, okay? And after that, we'll have a look at the solution together. All right, have you finished? Let's have a look at the solution together. Okay, so note here we have two methods to solve this question. First, let's have a look at method 1. We can let a vector n, whose components are n1, n2, be a common normal vector of L1 and L2. Note that the direction vector of L1 and L2 is m equals -6, 8 for both of the lines. Then we have the dot product between m and n, or n and m, equals 0, right? Which is equivalent to n1 times -6 plus n2 times 8 equals 0. Well, we can let n1 be 4 and n2 be 3, which means two components of n could be 4 and 3, right? Note that point A 1,5 is on L1, and a line perpendicular with L1 and then L2 and passes through point A is given by L3, which is 1,5 plus k times 4,3, where k belongs to the real number set. Then we can then let us find the intersection B, whose coordinates are B1, B2 between L3 and L2. So we can combine these two equations. 1 plus 4k equals 2 plus 9t, and 5 plus 3k equals 1 minus 12t. And we can find a pair of solutions for this system of two linear equations, which k equals -8 over 25 and t equals -19 over 25. So we can put k equals -8 over 25 into the equation of L3. Then the intersection between L3 and L2 is given by B1, which is 1 plus 4k equals 1 minus 4 times 8 over 25 equals -7 over 25. And B is given by 5 plus 3k equals 5 minus 3 times 8 over 25, which is 101 over 25. Then the distance between L1 and L2 is actually the magnitude of vector AB, right? The magnitude of vector AB is the difference of x component squared plus the difference between the y component squared. And then find the square root of this sum, which gives us 1.6. Well, actually, the method 1 is quite intuitive, right? If you find the coordinates for point A and coordinates of point B, then we can find the distance between A and B, which is the distance between the two lines. Okay, any questions? If you don't have any questions, let's have a look at another solution. So there is another method we can use to find the distance between two parallel lines. So we can let the vector n, whose components are n1 and 2, be a common normal vector of L1 and L2. Also note that the direction vector of L1 and L2 is m, which is -6 and 8. Then we have the dot product between n and m equals 0. So we can let n1 be 4 and n2 be 3. Therefore, we can find a common normal vector of L1 and L2. So basically, the first few steps are exactly the same with the previous method, right? Then we can find any 2 points P1 and P2 on L1 and L2 respectively, as shown here on the graph on the bottom right. For example, P1, according to the vector equation for both lines, we know P1, whose coordinates are 1, 5, must be on L1, and P2, whose coordinates are 2, 1, is on L2, right? As shown here in this graph. Then we know the vector P1, P2 is given by 1, -4. Then we know the distance between L1 and L2 is actually the magnitude of the projection of P1, P2 on the normal vector n, right? Can you see that? And previously, we have already learned that the magnitude of a projection of one vector on the other can be given by this formula, which is the magnitude of vector p1, p2 dot product with vector n over the magnitude of vector n. Okay, so the dot product between p1, p2, and n is given by 1 times 4 plus -4 times 3. And the magnitude of n is very easy to calculate, which is the square root of 4 squared plus 3 squared, which is 5, right? So if we put all the values in, that also gives us 1.6. So as you can see here, this method is much easier than the previous one, right? So that's why we have studied the projection of one vector on the other in previous lessons. We can use this conclusion here to find the distance between the two parallel lines. So let's make a summary. A main takeaway of this example question is the distance between two parallel lines can be calculated using this formula below. The distance between the two parallel lines can be given by the magnitude of vector p1, p2 with vector n over the magnitude of vector n, where p1 and p2 are any points on each line, respectively, and vector n is normal common to both lines. Okay, I'll give you 1 minute to have a look at this question and main takeaway. Probably you should write this down onto your notebook, okay? All right, if you don't have any questions, let's have a look at the intersections of lines in three-dimensional space. So given two lines in three space, there are four possibilities for the intersection of lines. So pay attention with the differences between the cases in two space and three space. So first, in three space, the lines can be distinct and intersect at a point. So there is exactly one solution. Second, the lines could also be coincident, so there are an infinite number of solutions, which means these two lines are actually the same, right? Third, the lines can also be parallel but distinct, so there is no solution. The distance between the two parallel lines is the length of the common perpendicular section between the two lines, right? And last, the lines are distinct but not parallel in three-dimensional space, and they do not intersect. These are called skew lines. For skew lines, there is no solution. And we can also calculate the distance between the two lines. The distance between the two skew lines is the length of the common perpendicular section between the two lines, which is also the shortest distance between the two lines. Okay, have a look at these relationships. Also, we can determine if two lines in three space intersect or not, or parallel or skew using their equations. Okay, have a look at these situations first, and then we'll have a look at some example questions to check your understandings of the intersections of lines in three space. All right, if you're finished, let's have a look at some example questions. Okay, determine if these lines intersect. If they do, find the coordinates of the point of intersection. Line L1 is given by xyz equals 5, 11, 2 plus s times 1, 5, negative 2. L2 is given by xyz is 1, negative 9, 9 plus t times 1, 5, negative 2. Okay, I'll give you 4 minutes to have a look at these questions. Okay, have you finished? Well, let's have a look at the solution together. Well, actually, there are two methods we can use to solve this question. So by observation of the vector equations for these lines, you can see the direction vectors are the same, right? So the two lines are parallel. Then we must determine if the lines are parallel and distinct or coincident. So in the first method, we can solve this question by verifying a point. If the lines are coincident, then the coordinates of the point 5, 11, 2 from line 1 will also satisfy the equation for L2, right? So we can write the parametric equations for L2 as x equals 1 plus t, y equals -9 plus 5t, z equals 9 minus 2t. Then we can substitute the coordinates of 5, 11, 2 and solve each equation for t. First equation gives us t equals 4. Second equation gives us t equals 4. And the third equation gives us t equals 3.5. So since the t values are not identical, that means we cannot find a single value for t that satisfy all of the three equations. Therefore, the point 5, 11, 12, which is on L1, does not lie on line 2. So which means the two lines are parallel and distinct, right? Otherwise, any point on L1 must lie on L2. Since the values of t are close to one another, we can imagine that the two lines are likely to be relatively close to each other. Okay, any questions? So that's the first method you can use to check the relationship between the two lines. Okay, next, let's have a look at the second method. We can also directly try to solve for an intersection point. We can write each equation in parametric form. And then we can let the x coordinate of L1 equals x coordinate of L2, y coordinate of L1 equals y coordinate of L2, z coordinate of L1 equals z coordinate of L2 to check if we can find a single pair of solutions to satisfy all of the equations, all of the three systems. So we can rearrange equation number 1 to isolate S. That gives us S equals t minus 4. Then we can substitute S equals t minus 4 into equation number 2 and 3 to solve for t, which gives us 0t equals 0 and 0t equals 1 respectively. So the equation 0t equals 1 has no solutions apparently, right? Therefore, we cannot find a pair of solutions of S and T to satisfy all of the equations. Therefore, the two lines must be parallel and distinct. Okay, have a look at this solution here. Do you have any questions? Oh, actually, you can choose either method here. Either method you like to solve a question like this. Okay. So if you don't have any questions, let's consider another example. Can you find the distance between the following two parallel lines? Well, in the previous question, we have already seen that these two lines, L1 and L2, are parallel and distinct, right? So now can you find the distance between the two parallel lines in three-dimensional space? Okay, I'll give you 4 minutes to have a look at the solution. Then we'll have a look at the solution together, okay? All right, have you finished? Let's have a look at the solution together. Okay, note that the direction vector of L1 is M1, whose components are 1, 5, -2, right? Well, which is actually the direction vector of L2. Then a plane perpendicular with L1 and L2 and passes through point A, which is on L1, is given by this equation, x plus 5y minus 2z plus d equals 0. Because M1 is normal vector of the plane pi, right? And point A is a point on L1. So from this equation of L1, we know a possible point for LA could be 5, 11, 2, right? Then put the coordinates of A into that equation, in which we can solve d equals -56. Therefore, the equation for this plane, which is shown here in this graph, can be given by this equation, x plus 5y minus 2z minus 56 equals 0. Then we can find the intersection point B, whose coordinates are B1, B2, B3, between line L2 and pi. So note that line L2, we can write the x, y, and z coordinates as 1 plus t plus 5 times -9 plus 5t minus 2 times the z coordinate of z component of L2, which is 9 minus 2t. You follow me? Then solve for t. T is 59 over 15. Then put t equals 59 over 15 into the equation of L2. Then we can find the coordinate of the intersection between L2 and pi, which is B1 equals 74 over 15, B2 equals 160 over 15, and B3 equals 17 over 15. Then if we know the coordinate of point A and coordinate of point B, we can find the distance between L1 and L2, which is actually the magnitude of vector A, B, which is given by square root of the sum of the differences between X, Y, and Z coordinates, which is given by approximately 0.9310. Okay, have a look at this solution here. Any questions, just let me know, okay? So this is how we can find the distance between two parallel lines in three-dimensional space. All right, if you don't have any questions, let's consider another example question. Okay, if you are given two lines that intersect at a single point as this, line L1 is xyz equals 7, 2 minus 6 plus s times 2, 1, -3. L2 is given by this vector equation. Can you find the point of intersection of line L1 and line L2? Okay, I'll give you 4 minutes to have a look at the solution by yourself first, okay? Okay, have you finished? And let's have a look at the solution together. Okay, note that the direction vector are not parallel, right? Which is 2, 1, -3, and 1, 5, 5. We can write the equations in parametric form. L1 has parametric equations like this, and L2 has parametric equations like this. Then we can equate expressions for like coordinates. X equals X, Y equals Y, and Z equals Z. So first, we can solve 2s minus t equals -4. Then s minus 5t equals 7. Then 3s plus 5t equals -19. We can solve equation number 2 and 3 for s and t. Of course, you can solve equation number 1 and 2 or 1 and 3 first. Okay. If you solve 2 and 3 first, that gives us s equals -3, t equals -2. Then check if this pair of solution can satisfy equation number 1. If you substitute the s and t into the equation number 1, you can find the left side of equation number 1 equals -4. And right side is also -4. Therefore, left side equals the right side. That means we can find a pair of solution. S equals -3, t equals -2, satisfying all of the 3 equations. Therefore, you can find a point of intersection by substituting s equals -3 into line 1 or t equals -2 into line 2. You can use either way. And the point of intersection is given by x, y, z equals 7 to -6 plus -3 times 2, 1, -3, which is 1, -1, and 3. So note that this is a position vector of that point, which means the coordinates of the point of intersection is 1, -1, 3. Okay, any questions? All right, if you don't have any questions, let's consider another example. Determine if these 2 lines are skew. Okay, can you recall the concept of skew lines, which we have already discussed here, right? In 3-dimensional space, if the lines are distinct but not parallel and they do not intersect, then they are called skew lines, which is shown here in this graph. Okay, so can you determine if these 2 lines are skew or not? Okay, I'll give you 5 minutes to have a look at the question by yourself first. Okay, you should have finished now. So let's have a look at solution together. Well, note that the direction vectors are not parallel for these two lines, right? Since the direction vector of L1, which is M1, is not equal to a scalar k times the direction vector M2, which is the direction vector of L2. Then we can write the equations in parametric form and equate the expressions for each variable. So x equals x, y equals y, and z equals z. That gives us three equations, 1, 2, 3. Again, we can solve either number 1, number 2, or number 2 and number 3, or number 1 and number 3 for t and s. So for example, we can first solve equation number 2 and number 3 for s and t. That gives us s equals -1, t equals 6. So check this pair of solution, s equals -1 and t equals +6 in equation number 1. The right side is -3, right? Left side equals -1 minus 2 times 6, which is -13, which does not equal to the right side. Thus, the lines do not intersect. Since the direction vectors are not parallel either, that means the two lines are not parallel. So if two lines are not parallel and they do not intersect in three-dimensional space, they are called skew lines, right? So these two lines are skewed. Okay, do you have any questions? All right, if you have no questions, let's have a look at a last example for today's lesson. Remember that for two skew lines, we can find direction between the skew lines, right? So if we know these two lines are skewed, can you find the distance between the two skew lines here? Well, now let's have a look at the last example here. So remember that the distance between the two skew lines is the length of the common perpendicular section between the two lines, which is also the shortest distance between the two lines. So now can you find a way to find the distance between the two skew lines? Okay, here I'm going to give you 4 minutes and have a look at this question by yourself first. Then we'll have a look at the solution together, okay? All right, then let's have a look at the solution together. So we can draw a diagram to illustrate the situation in this question, as shown here on the top right. Suppose section AB is a common perpendicular section between these two lines. So the length of AB is the distance between the two lines, right? Also note that AB is perpendicular to both L1 and L2. B is on L2, A is on L1. Then we also know, according to their vector positions, this point, 5, -4, -2, must be on L1, right? Let's denote that with P1. And the point 2, 0, 1 must be on L2. Let's use the letter P2 to denote this point. Since angle P1AB is 90 degrees, and angle P2BA is also 90 degrees. We know the projection of vector P1, P2 on vector N equals vector AB if N is any vector in the direction of AB, right? Well, N is a normal, sorry, N is any vector in the direction of AB. Thus, the magnitude of the projection of vector P1, P2 on vector N should equal the magnitude of vector AB, right? Which is the distance we are looking for. So next, that question converts to a question to find the magnitude of the projection of vector P1, P2 on vector N, right? Note vector N is any vector in the direction of AB, which is given by the magnitude of the dot product between vector P1, P2 with vector N over the magnitude of vector N. We have already know this formula in our previous lessons in the previous chapter, right? If you forget this formula, you can check the lesson in previous chapter. And then use position vectors to determine vector P1, P2. We know the coordinates of P1 and P2, right? Therefore, vector P1, P2 is given by 2, 0, 1, minus 5, -4, -2, which is -3, 4, +3. So you know the position vector of P1, P2. Also, we know the position of we know the position vector of the direction vector for both lines, right? We can use the direction vectors for both lines to calculate the normal vector to this line. Remember that the cross product of the two direction vectors for both lines give us the resultant vector, which is perpendicular to both lines, right? So note here, the cross product between M1 and M2, which are the direction vectors for both lines, can be calculated to 5, 5, -5, right? Remember, we can use the method here shown on the right to find the cross product, which is actually 5 times 1, 1, -1. So a vector normal to both lines can be chosen to be n equals 1, 1, -1. This vector here is perpendicular to both L1 and L2, right? Then we can find the magnitude of AB, which equals the dot product between P1, P2 with n over the magnitude of n, which is given by, well, you can put all the coordinates in. The final result is 2 square root of 3 over 3. Therefore, the perpendicular distance between these two lines is 2 square root of 3 over 3 units. Okay, so let's make a summary. The main takeaway of this example question is the distance between two skew lines can be calculated using this formula. D equals the magnitude of the projection of vector P1, P2 to vector N, which equals the magnitude of vector P1, P2 dot product with vector N over the magnitude of vector N, where P1 and P2 are any points on each line, and vector N equals M cross M2, M1 cross M2, which is normal common to both lines. Okay, have a look at this example here. Do you have any questions? Okay, so in the future, you can use this formula to calculate the distance between the two skew lines in three-dimensional space. All right, if you don't have any questions, that's the end of today's class. Remember to complete today's homework and submit them to Google Classroom before the deadline. Okay, I'll see you next time. Bye.